So the first, maybe the most important thing is with the weekly assignment. I put a problem on there that we haven't talked about yet, so I really apologize for that. So I'm gonna leave the assignment the same, but I'm just gonna push the due date back. I said originally that it was due today. Today we're gonna talk about what you need for number 3 on the assignment. So we haven't gotten to the material that you need for number 3 until today. We're going to push the due date back to Monday. And let's see what that is. The first. So I'm sorry about that. I know that's sort of frustrating, and you look at it and you're like, I have no idea how to do this. I apologize for that. But after today, you'll have everything you need to do that problem, and every other problem on there, you've seen what you need to do it. Anybody have any questions about that, the weekly assignment? Yeah.
Try to find the highest height.
Let me look at. Okay, so this is a projectile motion problem. You know that when it reaches the highest height, the y component of the velocity is going to be 0. Mm-hmm. So if you use that, it's pretty easy to find that. It's just a single equation. Yeah. Any other questions? With these weekly assignments, I'm happy to give little hints here and there, but I don't want to go through them the same way that I'm happy to go through like daily assignment problems, because to me, this is kind of one of the ways that I evaluate how well you're absorbing the material from the daily problems and from the lectures. Any other problems on the weekly assignment that anyone's getting stuck on? Okay. I don't know how this bar just came up here like this. I don't know. All right. Then let's get into so we've talked about using Newton's second law on individual objects, and then we talked about collections of bodies that are pushing or pulling on each other where everything has the same acceleration. And now we're going to talk about objects that are rolling or sliding. I mean, we've done things that are rolling and sliding before, but always before the surface they've been moving along has been horizontal. Now we're going to start doing ones where it's at an incline, okay? And what you'll see is that the rules we're going to use when it's at an incline are actually the same rules we used when it was horizontal. They kind of reduce to be the same thing. So rolling and sliding problems. So here's an example of the kind of thing we're going to do. If you have an object that's rolling along a surface like this, our starting point is we are going to choose a funny coordinate system for this. We haven't done this yet, not regularly at least, but we are going to always choose a coordinate system where the y-axis points directly out of the surface. So that's the y-axis. And then the x-axis is along the surface in whatever direction is required for this to be just like a rotated version of the normal coordinate system. Okay, so like if you start with a coordinate system like this, no matter how much you rotate it, you could never make the y-axis go up and the x-axis go like this. You would have to flip it at some point to make that happen, okay? So the x-axis, that's why the x-axis has to point along the incline. And so the rules are the y-axis points directly out of the surface. And that means that the x-axis is along the surface. Now, the orientation of the coordinate system is always a choice that you have when you're doing problems. You could orient the coordinate system at funny angles for any problem you want. We don't because it usually doesn't help in any way. So why does it help in problems like this to use this rotated coordinate system? So why do we use a rotated coordinate system for these? Well, let's think of the benefits. And the drawbacks. Make a pros and cons list. Okay, the first benefit is the acceleration is a lot simpler in this rotated coordinate system than it would be in the regular coordinate system. Since we always have the x-axis pointing along the surface and the object only slides or rolls along the surface, we can always represent the acceleration as a0. Okay, like notice if we didn't use a rotated coordinate system, this thing's acceleration is going to be along a line like that. So you'd have to use cosine and sine to figure out the direction of that acceleration. And that would be a pain, you know? And so by using this rotated coordinate system, we've simplified this one thing, okay? Then also, let's think about the forces that act. There's a normal force pushing up from the surface. And again, since the normal force is pointing towards the body straight out of the surface, we can always represent that as 0n. Okay, so once again, this is simple, whereas if we had used a normal coordinate system for this, it would be a complicated mix of sines and cosines. Okay, so that's two benefits. Then the third one is with sliding problems, we might have friction we have to deal with. the friction always acts along the surface, and so this is going to be plus or minus the coefficient of friction times the normal force for an x component, and then 0 for a y component. So all three of these things, if we used a non-rotated coordinate system, a regular coordinate system, we'd have cosines and sines in here for all of these. It's not like it's impossible, but it makes the math a lot more tedious for solving for the variables. We have nice simple forms because of that rotated coordinate system. There is one drawback, and that is the weight force. The weight has always been the easiest thing when we use a regular coordinate system because it points straight down. So if we had a coordinate system oriented like this, the normal orientation, then the weight force just goes in the negative y direction. But that's not the case anymore. You see, it's at like an angle with this coordinate system now, a vector that goes straight down. Are you with me on that? And so now we're going to have to represent the weight as like mg times the cosine of some angle, mg times the sine of some angle. So this is the one that gets messier. Well, you can see, I mean, we have these three things that get nicer, this one thing that gets uglier. Overall, it's in our, it's in our favor to make this switch. But it does mean we have to deal with this weight force. And one thing that I want you to notice is that this angle phi that we're going to use varies from 270 degrees by the angle the incline makes with horizontal. So all you have to do to come up with this angle is figure out, so you just have to determine whether you add or subtract from 270. Okay, so to do this, let's just do a couple of example problems. So let's say we have this cart moving along an incline that makes an angle of 20 degrees with the horizontal. And let's say this has a mass of 10 kilograms. And we want to know what's the acceleration. Well, our coordinate system is going to be this. And we know we're going to have to deal with that weight force, so I might as well start with that. So I'm going to draw the coordinate system over here at its angle. And then I'm going to draw the weight force. which is, the weight force is going to be the mass times 9.81. So this is 98.1 newtons. And this thing that I said to notice, this thing you need to remember is that however much this weight force deviates from the 270 degree line, that's this, is the angle that the incline makes with the horizontal. So we know that this is going to be 20 degrees. So what's the angle that we want to use with cosine and sine to represent this? Well, in order to come up with the components of this, you start at the positive x-axis and go all the way around until you hit the vector. So in this case, if you're starting with 270, should I be adding 20 to that or subtracting 20 from that? Adding, because you go 90, 180, you hit that 270 line, but then you have to go 20 degrees farther to get to the vector. Okay, so this angle phi, I'll call it, is 270 plus 20. So 290. And so the weight force is going to be cosine and sine of 290 degrees. Okay, so we always have to do the free body diagram. The weight force is 98.1. What other forces are acting on this body? Normal, yep, a pushing force from the ground. And that's not parallel to the weight force. It's perpendicular to the surface. Do you see that? There's no other forces acting on it, so now I can write out Newton's second law. 0, negative 98.1. Nope, that's exactly what you're not supposed to do. 98.1 times cosine and sine of 290 degrees. Plus, that normal force is in our y direction, so this is just 0n. That's how that normal force always shows up. And then these are equal to the mass, 10, times the acceleration. And the acceleration we'll write as a0. Okay, 98.1. So this weight force vector comes out to be oh, 33.52 for x, negative 92.18 for y, plus 0n is equal to 10 times a0. We want this acceleration vector. So all we need to do is solve for a. So the x equation says 33.52 is equal to 10a So A is equal to 3.35. Plug that into the acceleration vector, and you get that this acceleration vector is 3.35 for x, 0 for y. Or if you want to visualize the direction, it's in our positive x direction, which was down the ramp, 3.35. Any questions about that? Okay, let's do one with friction. So let's say that the ramp is going this way, and this angle is 30 degrees. And let's say this time it's a block sliding on the incline. Let's say the mass is 2 kilograms. And at the instant shown, let's say the block is moving down the ramp. So you can think of this as the direction of the velocity vector. That's the direction it's moving. We need that because, remember, the direction of the friction force is always opposite the direction that it's moving. And let's say that the coefficient of friction between the block and the ramp is 0.1. And we want to calculate the acceleration vector. Well, our coordinate system this time, take a second, you don't have to write anything down, but visualize. So the y-axis points straight out. Which way does the x-axis have to go in this picture? Yeah, it has to go, so the y-axis is this way. The x-axis this time has to go up the ramp. Anybody have any questions about that? So to figure out this angle, here's our coordinate system. The y-axis, or the weight force, goes straight down. This is the 270-degree line. That's the negative y-axis. And so this angle here has to be 30 degrees. So in this case, do we need to take 270 plus 30 or 270 minus 30? Minus. And that's because you start at the x-axis, you go 90, 180. If you do another 90 to get to 270, then you have to backtrack 30. So you can think of it as 270 minus 30 to get to here. You haven't gotten to the 270 line yet. And so this angle phi is 270 minus 30 degrees, or 240. Okay, now a free body diagram. We have the weight force of 19.62, a pushing force from the incline, N. At the instant shown, the block's velocity is down the ramp, so the friction force is up the ramp. And the magnitude of this is the coefficient, 0.1. times the normal force. So now we can write out Newton's second law. The weight force is 19.62 times the cosine of 240. 19.62 times the sine of 240. Plus the normal force in the y direction. Plus the friction force in the positive x direction, if you look at the direction of the coordinate system, coordinate axes. And all that is equal to the mass times the acceleration. And so for this one, we get negative 9.81 for the x component, negative 16.99 for the y component, plus 0n, plus 0.1n, 0 is equal to 2 times a0. Okay, just like before, this asks for the acceleration, so all we need to find the acceleration is this a. Okay, so you might think at first, okay, we just need the x equation, but remember that if we have friction, we have to figure out that n value first. So we'll use the y equation to find n, and then we'll use the n that we figured out in the x equation. Okay, so the y equation says negative 16.99 plus n is equal to 2 times 0. So n is equal to 16.99. Remember, the plain n is newtons, the fancy n is normal force. And now we'll go to the x equation and plug in the n value we just figured out. So the x equation says negative 9.81 plus 0.1 times 16.99 is equal to 2a. So negative 9.81 plus 0.1 times this is 1.7 if you round it, and that's equal to 2a. And so a comes out to be negative 4.06 meters per second squared. Now plug that a value back into the vector, and you get negative 4.060. Or if you want to visualize that direction, it's in the negative x direction. So it's this way with a magnitude of 4.06. So now, can we tell whether this is speeding up or slowing down? Yeah, we know the direction of the velocity is down the ramp. We just figured out the acceleration is also down the ramp, so it's speeding up. These are in the same direction. So it's speeding up. I didn't ask you when we did this first example on the wheels, I didn't ask you whether it was speeding up or slowing down. Can we tell whether this thing is speeding up or slowing down? We got an acceleration that was down the ramp. The answer is we can't, because I didn't give the direction of the velocity. And I didn't give the direction of the velocity because it didn't matter for any of our calculations. If at this instant the thing was rolling up the ramp, the acceleration would be down the ramp at 3.35 and it would be slowing down. If at this instant it was rolling down the ramp, the acceleration is still down the ramp at 3.35 and it would be speeding up. It's different though when you have friction because the direction of that friction force depended on which way it was moving. Okay? So with these friction problems, you can always figure out whether it's slowing down or speeding up. Let's do a similar problem. I guess, how do I want to do this? Let's say we have let's say we have a block like this. Mass is 1 kilogram. Let's say this angle is 15 degrees. And let's say at this instant it's sliding down the ramp. And let's think about what happens if you apply a force perpendicular to the surface like this. So let's say there's a, let me call this F. And we're first going to do this problem. Calculate the acceleration vector if F equals 0. And then second, we're going to calculate the acceleration vector if F equals 20 newtons. Okay, so first we're going to assume that force F isn't there, and second we're going to apply a force F. Anybody have any thoughts on whether this is going to affect the acceleration or not? I mean, that force is opposite the direction of the acceleration. So you might think, no, it won't. If it was a problem like this one, where there's no friction, and we applied a force perpendicular to the surface, it wouldn't have any effect on the acceleration. The math wouldn't notice it at all. But what we're going to see in this case is it does affect the acceleration when there's friction because that force is going to change the normal force, and that normal force is used to calculate the friction force. So the effect of pushing it into the surface increases the friction force. Okay? The harder you push the two things together, the more friction there is. And that makes sense if you think like, so if this object is sliding along the surface, you can see the friction catching. There's like a certain friction force, but now imagine that I put all my weight down on it and then tried to push it, okay? I'm not directly keeping it from moving. What I'm doing is increasing the amount that the cable has to push up on it, and that contact force between the two going up means the friction force goes up, okay? Okay, so the coordinate system has the y-axis like that, the x-axis along the surface. So if that's the weight force, this angle is 15 degrees. So the angle that we're going to use for the weight, is it going to be 270 plus or minus 15? Plus, yep. So we're going to use 285. Then the friction force, or the free body diagram, we have the weight. We have the normal force. The friction force is opposite the normal. I didn't give a coefficient. I have to give one to be able to do this problem, so let's call this 0.2. So this friction force is 0.2 times whatever the normal is. And we're going to start with that force F equal to 0, so I'm just going to leave it off. Now Newton's second law says 9.81 times the cosine and sine of 285 plus 0n plus that friction force is in the negative x direction. So negative 0.2n 0. And all that's equal to the mass times the acceleration. So this is 2.54 negative 9.48 plus 0n plus negative 0.2n 0 is equal to 1 times a0. First, I'll use the y equation to find n. Then I'll plug that into the x equation. And we get that A is equal to 0.64. plug that into the vector, and you get that the acceleration vector is 0.640. Or in other words, it's in the positive x direction. That's down the ramp at 0.64. Any questions on that? Okay, so that was part A. So now we're going to do part B, where we have this force applied. Okay, the free body diagram looks pretty similar. The only difference is now we have this new force F of 20 newtons that's pushing the surfaces closer together. And be really careful with these ends. It's so easy to get confused on these. These two ends are fancy. Those are normal forces. This end is plain. That's just saying that's 20 newtons. That's the units. Okay. Well, let's think about, okay, so we know that the friction force is going to be higher because those two surfaces are being pressed closer together. Okay, so if the friction force is higher, let's think about what's happening. In this first example, is this thing speeding up or slowing down for part A? It's speeding up because velocity and acceleration are in the same direction. If there's more friction, we expect it either to slow down less, so we expect to get a positive number of something less than 0.64, or it's actually going to start slowing down instead of speeding up, so we'd get a negative number. That's what we expect. Are you with me on that? Okay, so, and what about the weight force? Is that any different than in part A? All the angles are the same, the weight is the same, so the vector is going to be the same. So we have 2.54, negative 9.48, that's the weight force. Plus 0n, plus negative 0.2n, 0. And then what direction is that 20 Newton force in? Negative y, yep. So 0, negative 20 is equal to 1 times A0. We'll first use the y equation to figure out that pushing force between the incline and the block. So negative 9.48 plus n minus 20 is equal to 0. So n is equal to 29.48. Now the x equation says 2.54 minus 0.2 times 29.48 plus 0 is equal to A. And this time you get that A is equal to negative 3.36. Put that back in the acceleration vector and you get negative 3.360. Or in other words, the acceleration is up the ramp at 3.36. So it was speeding up in the first part. In the second part, the acceleration is opposite the velocity, meaning it's slowing down. Adding that extra contact force between the surface and the body made it slow down. Any questions about that? Okay, well, what if you're doing a rolling and sliding problem along a horizontal surface? Do we have to think in a new way about the coordinate system? I'm going to erase this in a second, but, oh, well, what am I going to do? So here's the surface. So what coordinate system are we going to use in this case? Yeah, it just comes out using the rules for rolling and sliding problems. We just end up back with our usual coordinate system. Okay? So notice if the incline is 0, you get the usual coordinate system. There's no reason that the acceleration has to be the thing that you calculate. From any one equation, you can solve for any one variable. So let's change it a little bit this time and say, okay, let's say there's a block with a mass of 10 kilograms. And let's say it's sliding down the incline. What coefficient of friction would we have to have so the block continues sliding with a constant velocity? The coordinate system has y-axis out of the surface. That means x-axis is up the incline. The weight force is like that. This angle is 25 degrees. And so is our angle 270 plus or 270 minus 25? Minus, yep. And so that is 245. Free body diagram. There's a weight force down of 98.1. there's a pushing force. It's sliding down the ramp. That means the friction force is up the ramp. And this time we don't know what this coefficient is, so I'm just going to write it in like this. We're going to be solving for that value mu. So now Newton's second law says 98.1 times the cosine of 245, 98.1 times the sine of 245, plus 0n. The friction force is in the positive x direction, so plus mu times n, 0. And that's equal to the mass times the acceleration. If this is moving with a constant velocity, right, we want to figure out what mu has to be for this to move with a constant velocity. What does that mean the acceleration is?
0.
0, yep. Acceleration is how quickly the velocity is changing. So 0 acceleration is the same thing as constant velocity. So this is just going to be the mass times 0, 0. So we get negative 41.46, negative 88.91, plus 0n, plus mu n 0 is equal to 0, 0. The y equation says negative 88.91 plus n is equal to 0. So n is equal to 88.91. And then plug that into the x equation. Negative 41.46 plus mu times 88.91 is equal to 0. So 88.91 mu is equal to 41.46. And so mu, in order for this to keep a constant velocity, has to be 0.466. What if the mu value was less than 0.466? Let's say the mu value was 0.3. Would this thing be, so it's not speeding up or slowing down when the velocity is constant, when the acceleration is 0. If this mu value was 0.3, would it be speeding up or slowing down? Speeding up, that's right. Friction always is trying to slow things down, so less friction means less is happening to slow it down, so it'll be speeding up. And if it's bigger than that, it'll be, if the friction force is bigger, the coefficient is bigger, then it'll be slowing down because there's more of something trying to slow it down. let me do one more example, sort of like a deluxe model that's using the last two things we've talked about. So this time, let's say we have these two carts. Connected by a cable. And we're, let's say this one has a mass of 4 kilograms. This one has a mass of 5 kilograms. And there's a force this way of, let's say, 20 newtons. And this angle is 20 degrees. And we want to know what's the acceleration vector of the carts. And then we want to calculate the tension in the cable. That's the magnitude of the force that cable is applying to each one of those bodies. Okay. This is on an incline, so we're going to use a coordinate system like this. The weight force is this way. So is this angle for the weight going to be 270 plus 20 or 270 minus 20? Plus, because you have to go all the way around past the 270. So now free body diagram. What do I want to isolate first? Now this is a system of bodies that have the same acceleration. They're moving as a single thing. So what's the rule for, like, what's the approach you want to use? The first thing you want to isolate. You want to isolate the whole system together. So I'm going to isolate both of these as a single thing. Okay. The total mass of the system is 9 kilograms. So the weight force is 88.29. The total pushing force, I'll call that N total. And then we have a force this way of 20 newtons. Newton's second law, so 88.29 times cosine and sine of 290 is 30.20, negative 82.97. N total is in the positive y. The 20 is in the negative x. And all that is equal to the total mass, 9, times the acceleration, a0. We want this acceleration vector, so I'm just going to use the x equation. So 30.2 minus 20 is equal to 9a. So 10.2 is equal to 9a. So a is equal to 1.13 repeating. So as a vector, the acceleration vector is 1.13 repeating, 0 for y, or down the ramp at 1.13. Any questions about the first part? Okay, so now we want to calculate the tension in the cable. Basically, we want to calculate either one, the cable force acting on either one of those two bodies. And the tension just means we're going to report the absolute value of it, the magnitude of the vector. So which one of those two do we want to isolate? Does it matter? It doesn't matter. We'd get the same thing no matter which one we did. Okay, so I guess I'll isolate the 4 kilogram. There's a weight force down of 4 times 9.81, so 39.24. There's a pushing force from the ground. I'll call that N4, just because it's a different variable than N total. Those are not going to have the same values. And what else, if you go around the boundary, where else do the surroundings make contact with the 4 kilogram? Bless you. Yeah, just at the cable. So there's a pulling force from the cable this way. And I'll call that T. And all we're trying to find, if you're looking for the tension, is we're trying to find the value of that T. So Newton's second law, we have 39.24 times the cosine of 290. 39.24 times the sine of 290. Plus 0 N4. The t is in the negative x direction, so plus negative t0. And that's equal to the mass, 4, times the acceleration vector that we know now, 1.13 repeating 0. So this is 13.42, negative 36.87, plus 0 N4, plus negative T0. The x equation says 13.42 minus t is equal to 4.53. And so T is equal to 8.89 newtons. And so what we know now is if for some reason you were going to set up a system like this and you wanted the cheapest, string or whatever that would still support these forces, we know that we would need a string that could support about 9 newtons of force, which is like if you go to the fishing supply store or whatever, they sell fishing line based on how much force it can support. Yes?
For B, it says what's the cable's tension? We found the tension, but then since we did 4, do we write negative or no negative?
No, just if it asks for tension, then you're just giving the magnitude of that value, and it'll always be positive. If it asks for the force vector the cable applies to the body, then you'd want to plug that into this force vector. And so you'd get a vector of negative 8.890. Yep.
So when you're building out the Newton's second law equation, if there's other forces like acting down on the objects, would you just add that like next to the T?
Yeah, exactly. Yeah, so in this case, if there was, don't write this on your notes, but I'm just going to write this. If there was a force coming down like this, say that was 50 newtons, you'd have another force vector that said 0, negative 50.
Yes. Cool.
Any other questions? Okay, let's stop there. So no labs this week, but the lab exam, the second lab exam is next week in lab. And so if you want to run through any problems or anything, I'll be over there. So feel free to come over. Yep.
What's going to be on the lab exam? Just the 2 labs we did? Or?
Everything before that too. Yeah, they're all cumulative. I guess let me get this in the notes before I leave. So lab exam 2 is going to be next week in lab. And yeah, remember that it's cumulative. So you should go back to the older stuff too. Okay, that's all.